Hello. In the last lecture, we have defined first fundamental form on regular surfaces. In this lecture, we'll be doing the following thing. Suppose if you take two surface patches and they overlap with each other, and from each of the surface patches, we get a first fundamental form. So we'll find a relation between the coefficients between those two fundamental forms. And after that, we'll define area of a region inside a surface. Okay, so let us begin. Let us take a regular surface S. And let us take two surface patches and let U sigma and U tilde sigma tilde be two surface patches such that this P, it is contained in the intersection of sigma U and sigma tilde U tilde. Okay, so corresponding to these two surface patches, we will have two first fundamental forms. So let E du square twice F du dv plus G dv square and E tilde du tilde square plus twice F tilde dv tilde plus G tilde dv tilde square are the first fundamental forms for this coordinate maps sigma ub and sigma tilde u tilde v tilde. Okay. Now, so this first fundamental form E du squared plus twice F du dv plus G dv squared will be written in this form. So E du square plus twice F du dv plus G dv square. So this is equal to du dv is this row matrix multiplied by this matrix EF FG multiplied by this column matrix du dv. Okay. And now if I take this map sigma tilde inverse compose sigma, okay, so this is a map from W to sigma tilde W. So what is this W? So the sigma, it is a map from this open set U to the surface. This is my sigma U. This might say U tilde, and I have a map sigma tilde, which takes this sigma U tilde to another open set sigma tilde U tilde, and sigma U intersect with sigma tilde U tilde, and here we have this point P. So I can find a W open set inside U such that sigma of this W, it will be contained in this intersection. Okay, so here it should be sigma tilde of sigma tilde inverse compose sigma W. Okay, so we have this map. So sigma tilde inverse of sigma of UB, this will be equal to U tilde P tilde. So this U tilde, it is a function of U and P. P tilde, it is a function of U and P. And sigma inverse compose sigma tilde applied on U tilde, V tilde is equal to U comma B. Okay. All right. So this U, it is a function of U tilde, V tilde, and B also, it is a function of U tilde, P tilde. And now if I take du, so it will be equal to del U tilde, du tilde plus del U del B tilde, dB tilde. And dB, it will be equal to dB du tilde plus dB, del B tilde, dV tilde. Okay, so I have these two equations, and now from here, so what I'll get, so from star equation, so what I'll get, E du square plus twice F du dB plus G dB square. So this will be equal to du tilde dB tilde multiplied by this matrix del U tilde del B del U tilde. Maybe I'll write it below. So this is equal to du tilde dB tilde del U tilde del B del U tilde del U del B tilde del B tilde multiplied by FG. Okay, and so here, so what you have, so you have the transpose of this matrix. Yeah, so this essentially, it is the Jacobian matrix. And this J here also it will be multiplied by this column matrix, the U tilde, D B tilde. Okay. So let us take this J to be this Jacobian matrix. So therefore, so what we have, so this first fundamental form, E du square plus twice F du dB plus G dV square. So this will be equal to du tilde dB tilde J transpose EFFG J du tilde dB tilde. Okay, so we have this thing here, and this will be equal to du tilde dB tilde E tilde F tilde F tilde G tilde du tilde dB tilde. So therefore, so this matrix, so E tilde F tilde F tilde G tilde, so this matrix, it will be equal to J transpose E F F G J. Okay, so therefore these coefficients E tilde F tilde F tilde G tilde, this will be related by this equation. Okay, all right. Now, my next goal is to define angle. Okay, so how do you define angle? So let us take a regular surface and let us take a point P, and let us take the tangent plane here. And in this tangent plane, we have two tangent vectors. And corresponding to these two tangent vectors, we'll get a curve in the surface. Suppose this is my alpha 1, and this blue curve, it is alpha 2. So what we have here, alpha 1 prime 0 is equal to P, and alpha 2 prime 0 is also equal to P. Okay. So how do you define angle between these two tangent vectors? So this is defined to be cos theta equal to inner product of alpha 1 prime 0 comma alpha 2 prime 0 divided by product of the norms of these two vectors, norm of alpha 1 prime 0 multiplied by norm of alpha 2 prime 0. So here I am assuming that both these tangent vectors are not equal to 0 vectors. Okay, so this theta give you the angle between these two tangent vectors, or more precisely, this theta, this angle theta is equal to cos inverse of this. Okay, all right. Now suppose these two curves alpha 1 and alpha 2 are my coordinate curves. So suppose alpha 1 and alpha 2 are coordinate curves. So that is this alpha 1 prime 0, it is equal to the tangent vector sigma u evaluated at the point P, and alpha 2 prime 0, it is sigma b evaluated at the point P. Okay, so then what is the angle between the coordinate vectors? So this is given by cos inverse inner product of sigma u with sigma b divided by norm of sigma u multiplied by norm of sigma b. Okay, and note that inner product of sigma u with sigma b is f. So this is cos inverse of f divided by root over. So E is the inner product of sigma u with sigma u. So E is equal to norm of sigma u square. So norm of sigma u is root of E, and norm of sigma b is root of f g. Okay, so therefore this will be the angle between the coordinate vectors. Okay, now let us come to the notion of area. So let us take, so let R be a bounded region in a regular surface patch u sigma. Okay, so suppose this is my surface S, and this is my u sigma or sigma u, and I have a bounded region R here. So we want to find the area of this region R. Okay. So now we have a map u from this sigma to sigma u. Okay, and now what you do, so you pull back this R in this u. So this is my sigma inverse R. Okay. So let us take, so let Q equal to sigma inverse R. Okay. Yeah. Now, how do I define the area of this region R? So area, so this is defined to be equal to the double integral Q of not of this vector, which is cross product of sigma u with sigma b, du db. So this is my definition of area. So area of R is defined by this double integral. Okay. Now, if I take another surface patch which also contains this R, so if u tilde sigma tilde be another surface patch such that R is also contained in this sigma tilde u tilde. Okay, so this implies that R is also contained, or sigma inverse, so sigma tilde inverse R is contained in u tilde. Okay. So now again let us take this map. So let H equals to sigma inverse compose sigma tilde. Okay. So let us take this map. So again, as before, u it will be function of this u tilde, v tilde. B will be function of also u tilde, p tilde. Okay. And if I take the Jacobian of this, okay. So corresponding to H, okay, I'll have a Jacobian matrix. So take the Jacobian matrix corresponding to H. So that is the Jacobian matrix is given by J equal to del u tilde, del u del b tilde, del v del u tilde, del b del b tilde. So we have this Jacobian matrix. And now if I take this integral, so let us take, so let q tilde to be equal to sigma tilde inverse of this R. And now if I take this double integral over q tilde, take the norm of this cross product, sigma tilde u tilde cross product with sigma tilde p tilde. Take the norm of this du tilde db tilde. So this will be equal to double integration q tilde norm of sigma u cross product with sigma b and then you have the determinant of the Jacobian matrix multiplied by du tilde db tilde. Okay, so why this is true? So you can check that this norm sigma tilde u tilde vector product with sigma tilde b tilde. So norm of this vector product, it is equal to norm of sigma u cross product with sigma b times determinant of the Jacobian matrix. So this is equal to del ub del u tilde b tilde times norm of sigma u vector product with sigma b. Take the norm of this. Okay, so we have this thing. Yeah. So now from this equation star, so this double integral q tilde norm of sigma tilde u tilde vector product with sigma tilde v tilde du tilde dv tilde. So this will be equal to double integral over q norm of the vector product sigma u with sigma b du db. So here I am applying the change of variable. So due to the change of variable, I have this equality. Okay. So therefore, so this area of this region R remains invariant under the change of surface patch. Okay. Now let us try to compute length of, area of a surface. So let us take torus. Example, area of torus. Okay. So let me recall what is my torus. So these are my coordinate axes. This is x-axis, this is y-axis, and this is z-axis. And so here I'll take a circle of radius r centered at a comma 0 comma 0. And now what you do, so you rotate this circle around z-axis. So you'll get a surface, and that is called to be torus. So this is my torus. Now you want to compute the area of this torus. Okay. So now let us take a parameterization of this torus. So let sigma u be, so this is equal to a plus r cos u cos b comma A plus R cos U sin B, comma, R sin U. Okay. So here this U is between 0 and 2 pi, and B also it is between 0 to 2 pi. Okay. So the torus, let us call this torus T. So this is my torus T. So this, in fact, it is equal to, if I just ignore the boundary point here, so 0, let us take 0 less than U less than 2 pi, and here 0 less than B less than 2 pi. And now, so this T, it will be equal to the sigma of closure of this interval 0 to pi cross 0 to pi. Okay. So here, let us observe this thing. Now you take this square. What is this square? So this vertex is 0, 0. This vertex is 2 pi, 0. This vertex is 2 pi, 2 pi, and this vertex is 0, 2 pi. Okay. All right. So this is my closed square. And if I just ignore the boundary of this square, so we'll get this inside region. We'll get this inside region. And you have a map sigma from this open square to this torus. This map is sigma. Okay. Now observe that where this boundary it is going under sigma. So if I take this two horizontal lines, if I take this two horizontal lines, so sigma you can extend it to the boundary of the square. So this horizontal line, it will go to a closed curve in the torus like this. And if I take this two vertical sides of the squares, this will go to a closed curve like this. Okay. So now let us take Q epsilon to be equal to this region. So UB belongs to R2 such that epsilon is less than U less than 2 pi minus epsilon, epsilon less than B less than 2 pi minus epsilon. So what is this Q epsilon in this figure? So this will be my Q epsilon. This region is Q epsilon, and let us take it to be closed. So then this will include this boundary also. Okay. So sigma of Q epsilon, it will be a region inside this T. Okay, it will be a closed region inside this T. So now I'll find the area of this sigma Q epsilon. So what will be the area of the sigma Q epsilon? So this, by the definition, is equal to double integral Q epsilon of norm of this vector product sigma u with sigma b du dv. So I have this thing here, and this norm of sigma u vector product with sigma b. So this will be equal to, you can find this will be equal to root over ej minus f square, or directly also you can find the norm of this vector product, which will be equal to r times r cos u plus a. So therefore, area of this sigma q epsilon, so this will be equal to the double integral q epsilon r times r cos u plus a du dv. This double integral, it is equal to the following: integration epsilon to 2 pi minus epsilon r square cos u plus a du times integration epsilon to 2 pi minus epsilon dv. You can compute this integration. So this will be equal to r square times 2 pi minus 2 epsilon sine 2 pi minus epsilon minus sine epsilon plus r a 2 pi minus 2 epsilon whole square. Okay. So now let us take, so let epsilon tends to 0. So area of this torus, so this will be equal to limit epsilon tends to 0, area of this sigma q epsilon. So this will be equal to 4 pi square r a. Okay. Yeah. So the area of this whole torus, it is equal to 4 pi square r a. Okay. So I'll stop here.